Hello and welcome to Late Night Space. Before settling in, take a quiet moment to like the video and subscribe to the channel. It helps this small, steady corner of the universe reach other nighttime listeners who are looking for something calm and unhurried. And if you'd like, leave a comment letting everyone know where you're watching or listening from tonight. Maybe beneath a clear sky where a few stars are visible. Maybe somewhere they're hidden by cloud or city light. Either way, above you, they are still burning. But somewhere else, one is not. Right now, in some distant corner of the universe, a star is reaching the end of its life. For millions or billions of years, it balanced gravity, pulling inward with nuclear fusion, pushing outward. Hydrogen fused into helium, light streamed into space. Planets may have orbited in quiet repetition. Then the fuel began to thin. The core contracted. Temperatures rose. Fusion changed. And eventually, the balance failed. What happens where a star dies? Does the space it occupied simply go dark? Is there an explosion? Does something remain in its place? Something heavier, denser, stranger? Astronomers have watched these endings unfold. The Hubble Space Telescope has captured expanding shells of glowing gas called planetary nebulae. Observatories have recorded the brilliant flash of supernovae outshining entire galaxies. Radio telescopes have detected the steady pulse of neutron stars, first discovered by Jocelyn Bell Burnell. And the Event Horizon Telescope has imaged the shadow of a black hole, the possible final state of a massive star's core. When a star dies, it does not simply disappear. Matter is rearranged. Gravity tightens its grip. Quantum mechanics pushes back. In some cases, the outer layers drift gently into space, forming delicate clouds of gas. In others, the collapse is violent, compressing a core to densities so extreme that atoms themselves cannot survive. The place where a star once shone becomes something new. Tonight, the journey moves toward those places, towards stellar remnants, collapsed cores, expanding nebulae, and the physics that governs them. Calmly, clearly, step by step, because the night sky feels stable. But every point of light has an ending. And where that ending happens, the universe becomes something extraordinary. Out in the dark, a star looks like a pinprick, a calm, steady dot that seems to promise permanence. But up close, a star is not a quiet object at all. It is a living contest between two relentless forces, fought inside a sphere of plasma so hot that atoms cannot stay intact. Electrons and nuclei move freely, and the whole structure is held together by gravity alone. No walls, no container, just mass pulling on itself, shaping itself, and refusing to let go. Gravity is the first ingredient. It is the reason anything gathers in the first place. In the cold reaches of a galaxy, giant clouds of gas and dust drift for ages, stirred by passing shockwaves, galactic tides, and the gentle push and pull of nearby stars. If part of a cloud becomes dense enough, gravity begins to win. It draws more gas inward. As the gas falls, it speeds up. As it compresses, it heats. This is not because space is warm, but because compression converts gravitational potential energy into thermal energy. The collapse is a kind of heating by squeezing, and the temperature climbs as the material piles up in the center. At first, the forming star is more like a gathering storm than a finished object. The gas continues to fall inward, but it does not fall perfectly straight. Even a tiny amount of rotation in the original cloud becomes important as the cloud shrinks. The rotation speeds up, and material flattens into a disk around the growing core. In many systems, this disk becomes the birthplace of planets. But long before planets have any chance to settle into neat orbits, the central object is already preparing for its true defining feature: nuclear fusion. Fusion begins when the core becomes hot and dense enough that nuclei collide with sufficient energy to overcome their electrical repulsion. Hydrogen nuclei carry positive charge. They naturally push each other away. Getting them close enough to fuse requires extreme conditions. When those conditions are finally reached, something fundamental happens. 4 hydrogen nuclei, through a chain of steps, become one helium nucleus. In the process, a small amount of mass is converted into energy. This is one of the most important ideas in modern physics, and it can be stated simply. Energy equals mass times the speed of light squared. That relation, introduced by Albert Einstein, explains why stars can shine so powerfully for so long. The speed of light squared is a staggeringly large multiplier, so even a tiny loss of mass becomes an immense release of energy. In a star like the Sun, this happens continuously, moment after moment, for billions of years. But the energy does not just appear and politely drift outward. It presses, it heats, it pushes. And that pushing is essential because gravity never stops trying to compress the star further. A stable star exists because it finds a balance between inward gravitational pull and outward pressure from hot gas and radiation. This balance is called hydrostatic equilibrium. Hydrostatic equilibrium is not a statue-like stillness. It is a living stability. If a star's core compresses slightly, temperature rises. Fusion rates increase. More energy flows outward. Pressure strengthens. The star expands a little and cools, which slows fusion back down. If the core expands too much, it cools. Fusion slows, pressure weakens, and gravity pulls it inward again. A star is, in a very real sense, a self-regulating engine. It adjusts its own behavior through feedback, guided by the laws of thermodynamics and the temperature sensitivity of nuclear reactions. For most of a star's life, this balance holds. It shines. It remains in a relatively steady state. And yet, even during this long, calm phase, the star is changing. Not in a way that is obvious on a human timescale, but in a way that is inexorable. Every fusion reaction alters the composition of the core. Hydrogen becomes helium. The fuel supply shifts. The internal structure evolves. The detailed understanding of how stars power themselves owes a great deal to the physicist Hans Bethe, who worked out the major fusion pathways in the 1930s. In stars like the Sun, the dominant process is the proton-proton chain. In this sequence, hydrogen nuclei fuse through a series of steps, ultimately producing helium, releasing energy, and emitting neutrinos. Neutrinos are elusive particles that rarely interact with matter. They stream out of the star almost immediately, carrying away a portion of the energy and giving astrophysicists a unique window into what is happening deep inside stellar cores. In heavier stars, the dominant process is the carbon-nitrogen-oxygen cycle, often called the CNO cycle. It still converts hydrogen into helium, but it uses carbon, nitrogen, and oxygen as catalysts. These elements are not consumed overall. They help the reaction proceed more efficiently at higher temperatures. The key distinction is that the CNO cycle becomes extremely sensitive to temperature. Raise the temperature a bit, and the fusion rate rises sharply. This is one reason massive stars are so luminous. Their core temperatures are higher, and their fusion engines run at a much faster pace. So mass matters from the beginning. It determines core pressure. Core pressure determines core temperature. Core temperature controls which fusion pathway dominates and how quickly fuel is consumed. And fuel consumption rate sets the clock for a star's lifespan. This is one of the most important and slightly unfair truths in astrophysics. The bigger the star, the shorter its life. Massive stars have more fuel, yes, but they spend it with shocking extravagance. Their gravity compresses their cores so strongly that fusion roars. They shine brilliantly, but they burn out quickly. Smaller stars, especially red dwarfs, sip their fuel slowly. They can remain stable for trillions of years. Energy generated in the core must travel outward to escape into space, and that journey is surprisingly difficult. Inside a star, matter is dense. Photons, the particles of light, do not simply shoot straight out. They are absorbed and re-emitted, scattered and redirected over and over again. In regions where energy moves primarily through radiation, the energy is carried by photons diffusing outward through countless interactions. The overall motion is outward, but the path is a chaotic zigzag. In a star like the Sun, a photon created in the core can take an extraordinarily long time to reach the surface, not because it is slow, but because it is constantly interrupted. In other regions, energy is transported by convection. Convection is the physical motion of material itself. Hot plasma rises, cooler plasma sinks. The star becomes a churning system of circulating flows. Convection tends to happen when the temperature gradient is steep enough that radiative diffusion cannot carry energy outward efficiently. The result is a star with internal layers that behave differently. Some zones are radiative, some are convective, and the pattern depends heavily on mass. All of this is still part of the long, steady middle of a star's life. The star shines because fusion provides energy. Energy provides pressure, and pressure balances gravity. Hydrostatic equilibrium holds the structure together, but the core is quietly changing composition, and composition matters because fusion depends on what fuel is available. Over time, hydrogen in the core is depleted. Helium accumulates. As the fraction of hydrogen drops, the fusion rate in the core begins to decrease. The outward pressure weakens. Gravity responds immediately because gravity does not wait patiently. It begins to compress the core again. Compression raises temperature. The star tries to compensate. And for a while, it often succeeds. The core becomes hotter and denser, which can keep hydrogen fusion going for longer. The star maintains stability, but it does so by tightening its own core. This is the beginning of a theme that will eventually lead to death. When fusion cannot keep up, gravity compresses the core, temperature rises, and new stages of fusion may ignite. The star evolves by climbing to higher temperatures, moving to new fuels. It is not choosing this path. It is being pushed along by gravity and the consequences of burning its original fuel. At this point, it helps to clarify something that can feel counterintuitive. A star does not have one uniform temperature. The surface of the Sun is only a few thousand degrees in temperature, while the core is many millions of degrees. In massive stars, core temperatures become even higher. Fusion is confined to the hottest central regions, because only there do nuclei collide with enough energy to fuse. the outer layers are not burning fuel the same way. They are responding to what the core is doing, swelling and contracting as internal pressure changes. As hydrogen in the central core declines, hydrogen fusion often continues in a shell surrounding the core. This is called shell burning. The core itself, now mostly helium, contracts. Surrounding it, a shell of hydrogen becomes the main fusion region. This rearrangement changes the star's structure. It often causes the outer layers to expand, making the star larger and cooler at the surface. It can become a red giant or supergiant depending on mass. But the important point here is the pattern. Core fuel is exhausted, the core contracts, shell burning begins, and the star's outer layers respond dramatically. None of this is sudden on human timescales. It is slow, grand, and mostly invisible without careful measurement. But in physics terms, it is a star beginning to drift away from its main stable phase. The long era of balance continues, but the balance is becoming harder to maintain. Instability is not chaos yet. It is a growing tension. The science of stellar structure and evolution developed through a mixture of theory, observation, and careful comparison. One of the most useful tools in astronomy is the Hertzsprung-Russell diagram, which plots stars by luminosity and surface temperature. When astronomers look at star clusters, they find that stars of different masses occupy predictable regions on this diagram, and that clusters of different ages show different patterns. This provides strong evidence that stars evolve in mass-dependent ways. Theoretical models built from the equations of hydrostatic equilibrium, energy generation, and energy transport reproduce these observed patterns with remarkable success. The more closely one looks, the clearer it becomes that a star's life is a sequence of negotiated compromises. Gravity compresses, fusion pushes back, energy moves outward, composition shifts, the star adjusts. For a long time it remains stable enough to look eternal. But the internal bookkeeping never stops. Hydrogen is steadily being converted into helium. The core is changing into something new. And eventually, the star will reach a point where a simple, hydrogen-burning core is no longer possible. That transition is not the end, but it is the beginning of the end game. Once the star can no longer rely on its original fuel in its original place, it must either find new ways to generate pressure or surrender to deeper collapse. What happens next depends overwhelmingly on mass, because mass determines how far gravity can push the star, how hot the core can become, and what new fusion stages can ignite. To understand how a star dies, it is necessary to understand how it spends its life. So the focus now narrows to the engine itself, and to what happens as that engine begins to change its fuel source, step by step, while gravity patiently waits for any sign of weakness. In the steady phase of a star like the Sun, the core temperature is high enough for hydrogen fusion, but not high enough for helium fusion to proceed efficiently. Helium nuclei carry more charge than hydrogen nuclei. They repel each other more strongly. Fusing helium requires higher temperatures, so when the core becomes helium-rich, the core does not immediately start fusing helium. It contracts. The contraction heats it. The star attempts to climb to the next rung of nuclear burning. Whether it reaches that rung depends on mass and on the quantum mechanical behavior of matter at extreme densities. This is where another crucial idea enters: degeneracy pressure. Degeneracy pressure is not ordinary pressure from heat. It is a quantum mechanical effect that arises because certain particles cannot be packed into identical states. In simple terms, there is a kind of crowding limit built into the laws of quantum physics. When matter becomes extremely dense, this crowding limit produces a pressure that can resist further compression, even if the matter is not very hot. Electron degeneracy pressure is especially important for the later lives of stars. As a stellar core contracts and becomes denser, electrons are forced into higher and higher energy states. The resulting pressure resists compression. This quantum pressure can support a star's core when thermal pressure from fusion is no longer adequate. The significance of this was explored in depth by Subrahmanyan Chandra X, whose work on the structure of compact stellar remnants revealed that there is a maximum mass that electron degeneracy pressure can support. Above that mass, the core cannot remain a stable white dwarf. It must collapse further. That limit, known as the Chandra X limit, becomes a decisive boundary in the fate of stars. It is one of the reasons mass is not just important, but absolutely defining. Even before reaching those dramatic endpoints, degeneracy pressure influences how stars behave as they run out of fuel. For stars of relatively modest mass, the helium core can become partially supported by electron degeneracy pressure before helium fusion begins. This changes how helium ignition occurs. For higher mass stars, cores remain hot enough that degeneracy pressure plays a different role. The details vary, but the underlying principle remains. As fuel changes and contraction begins, quantum mechanics becomes more than a footnote. It becomes structural. Returning to the process at hand, the key moment is this. Hydrogen in the core is being replaced by helium. Fusion in the core slows. Gravity compresses the core. Temperature rises. Hydrogen fusion may continue in a shell, which can actually increase the star's overall luminosity, even though the core itself is no longer producing energy the same way. The star looks brighter and larger. From the outside, it may appear to be thriving. Inside, the core is tightening, growing hotter, and becoming denser. Energy transport adjusts as well. As the star's internal temperature gradients change, convective zones may shift. In many stars, convection becomes more dominant in the expanded outer layers, while radiative transport remains important in other regions. The star becomes a layered structure with different behaviors in different shells. It is a physical system with multiple regimes operating at once, all tied together by gravity's insistence on inward pull. This is the slow approach to instability, and it is worth emphasizing how calm it is. There is no sudden alarm bell. There is no single dramatic moment that announces, clearly and loudly, that a star has begun to die. Instead, the star steadily rearranges itself to keep pressure support. When one fuel runs low, gravity compresses the core until a new fuel can ignite, or until quantum pressure halts further compression. The star's death, in many cases, is not a single event. It is a sequence of transitions, each one shaped by mass, composition, and the interplay between thermodynamics and quantum physics. The central takeaway is simple and powerful. A star is born when gravity compresses gas until fusion ignites. A star lives by maintaining hydrostatic equilibrium, balancing gravity with pressure produced by fusion-generated heat and radiation. A star evolves because fusion changes the core's composition, gradually altering the conditions that make equilibrium possible. And the earliest sign of the end is not dimming, it is change. Fuel depletion in the core begins a process of contraction, heating, shell burning, and structural transformation. From here, the story becomes more specific. The next stages depend on mass, and mass splits the universe of stars into different destinies. Some will swell and shed their outer layers gently, leaving behind compact cores supported by quantum pressure. Others will push onward into heavier fusion stages, building more complex internal shells until they reach iron, where fusion can no longer provide support. In the most massive cases, collapse becomes violent, and the place where the star lived becomes something almost impossible to imagine. But every path begins with the same foundational physics, repeated across the cosmos with quiet consistency. Gravity gathers, fusion ignites, pressure pushes back, energy flows outward, fuel is consumed, the core changes. Balance becomes harder to maintain, and once balance begins to slip, a star's surroundings are no longer just a stage. They become part of the outcome. Because when a star finally dies, what matters is not only what happens to the star itself, but what happens to the region of space it leaves behind. Not every star ends with a bang loud enough to rattle a galaxy. Some stars die the way an old lamp dies. The filament does not explode. The room does not shake. The light simply becomes a little weaker, a little redder, a little more tired, until one evening it fails to brighten at all. There is still a lamp. There is still a room. But the thing that once turned electricity into light has quietly reached the end of what it can do. In astrophysics, that quieter ending belongs to most stars in the universe. The reason is simple. Most stars are small. The Milky Way is packed with low-mass stars, especially red dwarfs, and those stars set the tempo for the calm side of stellar death. They burn hydrogen slowly, almost conservatively, and they can keep going for a very long time. A low-mass star is not just a smaller version of the Sun. It behaves differently on the inside. Its core does not run as hot, so nuclear fusion proceeds at a slower pace. Many red dwarfs are also strongly convective, meaning the star churns and mixes material throughout much of its interior. That mixing matters because it keeps bringing fresh hydrogen into regions where fusion can continue. It is one reason red dwarfs are so efficient with their fuel. The result is a long, steady life. A red dwarf does not rush. It does not blaze. It glows. And because the universe itself is only about 13.8 billion years old, many red dwarfs have not had time to die yet. They are still in their long middle age, steadily converting hydrogen into helium. The quiet deaths of small stars mostly belong to the future, written in theory and models that extend far beyond the current age of the cosmos. Still, the general outline is well understood. As even a small star gradually converts its central hydrogen into helium, the core composition changes. The star begins to adjust. Fusion may migrate outward into a shell surrounding a helium-rich core. Gravity responds to the changing pressure balance by compressing the core slightly, raising its temperature. The outer layers respond by expanding. The star becomes larger and cooler at the surface, shifting toward redder light. For stars closer to the Sun's mass, this shift can become dramatic. The star swells into a red giant. The red giant phase is one of the strangest moments in a star's life because it looks, from the outside, like a sudden growth spurt. The star's radius can expand enormously. Its surface cools, so it glows red-orange rather than white-yellow. Yet the star's total luminosity often increases, even though the core is no longer fusing hydrogen in the same central way. This apparent contradiction makes sense once the internal structure is imagined as layers. A contracting, helium-rich core sits at the center. Around it, a shell of hydrogen becomes the dominant fusion region. That shell can burn fiercely because the contracting core raises the temperature and pressure just outside it. The energy output from shell burning forces the star's outer layers to puff outward like a balloon being warmed. In our own solar system, the Sun is expected to enter a red giant phase in the far future. The details depend on complex interactions between mass loss, internal mixing, and the precise rate of shell burning. But the broad picture is clear. The Sun will not remain as it is. One day it will expand and brighten, and the inner solar system will become a much harsher place. For medium-mass stars, the red giant phase is also the doorway to one of the most famous and misunderstood events in stellar evolution, the helium flash. To understand the helium flash, it helps to remember what helium is in nuclear terms. Helium nuclei have a charge of 2, meaning they repel each other more strongly than hydrogen nuclei do. Fusing helium requires higher temperatures than fusing hydrogen. So when a star builds up a helium-rich core, it cannot immediately begin helium fusion at ordinary main sequence core temperatures. The core contracts under gravity, growing denser and hotter, trying to reach the conditions required for helium fusion. In stars around the Sun's mass, something else happens during that contraction. The core becomes so dense that it begins to be supported partly by electron degeneracy pressure, a quantum mechanical effect that resists compression. Degeneracy pressure does not depend on temperature in the same way ordinary gas pressure does. That matters because it means the core can continue contracting and heating without expanding in response. The usual self-regulating behavior is weakened, so the core heats up quietly, without the same gentle expansion that would normally relieve pressure. It becomes a tightly packed electron-degenerate ball of helium, squeezed by gravity and surrounded by a shell of hydrogen fusion. Eventually, the core reaches the temperature at which helium fusion can ignite. Helium fusion in these conditions begins through the triple alpha process, where helium nuclei combine in steps to form carbon. When helium ignition happens in a degenerate core, it can surge rapidly. The fusion rate skyrockets in a short time because temperature rises, and rising temperature boosts fusion, and the core does not initially expand to cool itself. That runaway ignition is the helium flash. The phrase sounds like something that should light up the galaxy. It sounds like a star briefly turning into a beacon, but the helium flash is mostly hidden inside the star. It does not produce a brilliant visible flare from the surface. The energy released goes into lifting the degeneracy, expanding the core, and rearranging the star's internal structure. It is like a sudden internal reset. The star survives. The star does not explode, it simply changes. After the helium flash, the star settles into a new stable phase. Helium fusion proceeds more steadily in the core, converting helium into carbon and oxygen. Hydrogen fusion continues in a surrounding shell. The star's luminosity and radius adjust again. In many cases, it becomes somewhat less swollen than at its maximum red giant expansion, though it remains far from its original main sequence size. From a human perspective, this is already an extraordinary story. A star spends billions of years in a stable balance, then gradually transforms into a huge, cooler red giant ignites helium in its core through a sudden internal flash and continues shining with a new internal engine. But the quiet death still lies ahead. Once the star's core helium is depleted, the situation repeats in a new form. The core becomes rich in carbon and oxygen. Fusion shifts to shells again. The star can ascend the red giant branch again, often entering what is called the asymptotic giant branch, a phase characterized by layered shell burning and powerful pulsations. In this late stage, the star becomes bloated and luminous, with a very extended, loosely bound envelope. The gravity at the surface is weak, and the outer layers can be lifted and pushed outward by radiation pressure, stellar pulsations, and strong stellar winds. The star begins to lose mass in earnest, shedding its outer layers into surrounding space. This shedding is where the idea of a star dying quietly becomes literal. The star does not need to explode to transform its surroundings. It can simply exhale. Over time, the star's outer layers drift away, forming an expanding shell of gas. This gas moves outward into interstellar space, carrying with it elements produced during the star's life, including carbon, nitrogen, and other products of stellar nucleosynthesis. The star enriches the galaxy with the materials that will later become part of new stars, planets, and perhaps living chemistry. As the outer layers thin out and move away, the star's hot core becomes exposed. That core is compact and extremely hot, even if it is not very large. It emits strong ultraviolet radiation, and that ultraviolet light ionizes the expanding gas shell. The gas begins to glow. This is the birth of a planetary nebula. The name is historical, not physical. Early astronomers using small telescopes saw these objects as faint, rounded, planet-like disks, and the name stuck. Planetary nebulae have nothing to do with planets. They are the luminous, ionized shells of gas ejected by dying stars of modest mass. A planetary nebula can be breathtaking. Some are nearly spherical, like delicate cosmic bubbles. Others are bipolar, with hourglass shapes and striking symmetry. Many show intricate filaments, knots, and arcs, shaped by stellar winds, magnetic fields, and the presence of companion stars. The details vary, but the underlying story is consistent. The star has shed its outer envelope, and the exposed core is lighting up the departing gas like a lantern shining through fog. This is one of the clearest answers to the question of what happens where a star dies. The place where the star once shone becomes a glowing cloud. Not a sudden blast wave, but a slowly expanding halo of illuminated gas, drifting outward at tens of kilometers per second. The core remains at the center, steadily fading in luminosity as it no longer has fusion to replenish its heat. Some of the most iconic images of planetary nebulae come from the Hubble Space Telescope. Hubble's sharp vision above Earth's atmosphere has captured objects like the Helix Nebula, which looks like a vast eye in space, and the Ring Nebula, a glowing torus of gas. These images are not just pretty. They reveal structure, temperature differences, and chemical composition through different filters and wavelengths. They show that a quiet, stellar death can still sculpt space with remarkable artistry. And yet, the planetary nebula phase is short by astronomical standards. The glowing gas shell expands and thins. Over tens of thousands of years, it disperses into the interstellar medium. The glow fades as the gas becomes too diffuse to remain brightly ionized. What remains at the center is the true remnant of the star. The remnant is a white dwarf. A white dwarf is the exposed core left behind after a modest star loses its outer layers. It is typically comparable in size to Earth, but with a mass comparable to the Sun. That means it is extraordinarily dense. It is supported against gravity not by fusion, but by electron degeneracy pressure, the quantum mechanical effect that resists compressing electrons into identical states. Even without describing the mathematics, the physical idea is striking. The white dwarf is a stellar corpse held up by quantum rules. At first, a newly formed white dwarf is very hot. It glows not because it is producing new energy, but because it is radiating away stored thermal energy. Over billions of years, it cools. Slowly, patiently, like a coal that remains warm long after the fire has gone out. So the quiet death of a medium star is not a single moment. It is a long process of transformation. A steady main sequence star becomes a red giant. It ignites helium. It grows and pulses. It sheds its atmosphere into space. It lights up that gas into a planetary nebula. Then it leaves behind a white dwarf that cools for the rest of cosmic time. Now, consider what this means for the surrounding region of space. The place where the star dies is not empty afterward. It is enriched. It is altered. The expanding gas carries heavy elements outward, mixing into the interstellar medium. That material can later become part of new stars and planets. The death of a star can literally seed the ingredients for new worlds. This is why astronomers sometimes say that stars are not just lights in the sky. They are chemical engines. They build elements over time, then release them back into the galaxy. Even a quiet death contributes to the ongoing recycling of matter. There is another layer of quiet drama here too. In many cases, the shape of a planetary nebula suggests that the star was not alone. A companion star orbiting nearby can influence the outflow of gas, producing spirals, jets, or bipolar lobes. The star's death becomes a gravitational dance, shaping the departing atmosphere into complex forms. Some planetary nebulae show hints of this story in their structure. Symmetry that suggests an orbit, arcs that suggest periodic mass loss, and bright knots where winds collide. Hubble images often reveal these details with clarity that ground-based telescopes struggle to match. The telescope's ability to see fine structures has turned planetary nebulae into laboratories for studying late-stage stellar winds, gas dynamics, and the interaction between radiation and matter. So when asked what happens where a star dies, one answer is unexpectedly gentle. Space is not shattered. It is painted. The star's outer layers become an expanding cloud. Ultraviolet radiation makes the cloud glow. The glow fades as the gas disperses. A white dwarf remains. The region becomes chemically richer than before. It becomes part of the galaxy's long-term evolution. And this is the contrast that makes the next kind of stellar death feel almost shocking. Because once the quiet path is understood, the violent path becomes clearer. It is not violence for its own sake. It is what happens when mass changes the rules. It is what happens when gravity becomes so strong and fusion so brief that the star cannot ease itself into a gentle farewell. But for now, there is something almost comforting in the quiet endings. The universe is not always explosive. Sometimes it is patient. Sometimes it lets a star spend its last energy on a soft glow, drifting outward into the dark, leaving behind a compact ember of quantum-supported matter and a faintly illuminated shell that slowly dissolves into the space between stars. In those moments, stellar death looks less like destruction and more like a kind of cosmic breathing. A long inhale of gravity and fusion, and then, at the end, a slow exhale of gas and light into the galaxy that raised the star in the first place. After a star has shed its outer layers, after the last shimmering threads of a planetary nebula begin to thin and dissolve into the surrounding interstellar medium, something small and intensely stubborn is left behind at the center. It does not look like a star anymore. It no longer has the sprawling, glowing envelope that once filled space with warmth and light, and it no longer has a furnace in its core, steadily turning fresh fuel into new energy. What remains is the exposed core compressed into a compact object about the size of Earth, yet containing a mass comparable to the Sun. This is a white dwarf, and the fact that such an object can exist at all is one of the quiet miracles of physics. A white dwarf is not supported by the heat of fusion. In an ordinary star, the core's heat creates pressure, and that pressure pushes outward to balance gravity's inward pull. Remove fusion, and the heat source fades. Gravity should win. The core should continue collapsing. But it does not. Not immediately. Not for many stars. The reason is that matter behaves differently when it is squeezed to extreme densities. At the heart of a white dwarf is a form of pressure that does not come from warmth and does not depend on how hot the material is. It comes from quantum mechanics itself. It comes from a rule so basic, so deeply stitched into the universe, that it is easy to underestimate its power until it holds up a dead star. This rule is called the Pauli exclusion principle. It applies to particles known as fermions, including electrons. In simple terms, it says that identical electrons cannot all occupy the same quantum state. They cannot be stacked into the same exact set of properties and conditions, like identical coins forced into the same slot. So what happens when gravity tries to crush a stellar core until electrons are packed impossibly close together? The electrons resist. Not through heat, not through chemical bonds, not through ordinary stiffness. They resist through the demand for distinctness. If electrons cannot share the same state, then forcing them into a smaller volume means they must occupy higher and higher energy states. That increase in energy creates a pressure, a degeneracy pressure. It is called electron degeneracy pressure. This is the first great lesson of a white dwarf. Even when a star's furnace dies, physics does not run out of ways to push back. Electron degeneracy pressure can become strong enough to halt collapse, at least for cores below a certain mass. Gravity squeezes. The electrons push back. The result is a compact, stable remnant, a white dwarf, quietly sitting at the center of what used to be a star. The strange part is that this pressure does not need the star to be hot. A white dwarf can cool for billions of years and still remain supported. That is not how most people picture pressure. In everyday life, pressure usually comes from motion, from heat, from particles bouncing around. But degeneracy pressure comes from the structure of quantum states. It is pressure built from the rules of identity. This is where Subrahmanyan Chandrasekhar enters the story. In the early 20th century, Chandrasekhar studied what would happen to these compact stellar remnants as they became more massive. He combined ideas from quantum mechanics with the physics of gravity and the behavior of matter at high density. And he found something startling. There is a limit to how much mass electron degeneracy pressure can support. Below that limit, a white dwarf can exist as a stable object. Above it, the core cannot hold itself up. Gravity overwhelms the quantum support, and the remnant must collapse further into something even denser. That threshold is known as the Chandra X limit. In rough terms, it is about 1.4 times the mass of the Sun. It is not a perfectly fixed number for every circumstance, because composition and rotation can adjust details, but the core idea is strong and widely accepted. There is a maximum mass for a stable white dwarf. What makes this limit so powerful is that it draws a bright line through stellar fate. It means that some dying stars can end as white dwarfs, while others cannot, even if they try. It also means that if a white dwarf gains mass later, perhaps by pulling gas from a nearby companion star in a binary system, it can be pushed toward instability again. The white dwarf can be forced back onto the edge of collapse, and that edge is not gentle. But before that more violent path is considered, it helps to stay with the white dwarf itself, because it is an object that tells the truth about what a star becomes when fusion is gone. Inside a typical white dwarf, the core is composed mostly of carbon and oxygen. These elements were formed during the later fusion stages of the star's life, and then left behind when further fusion became impossible. The carbon and oxygen nuclei sit in an extremely dense arrangement, embedded in a sea of degenerate electrons. The electrons provide most of the pressure support. The nuclei, heavy and closely packed, contribute most of the mass. The white dwarf is, in a sense, an exposed stellar skeleton. All the soft outer layers are gone. The glowing atmosphere is thin. The core is laid bare, and gravity has compressed it to a density that makes ordinary intuition useless. That density is not just an interesting statistic. It has consequences. A white dwarf's surface gravity is immense. If a person could stand there, which they cannot, the weight would be crushing beyond imagination. The object is compact enough that its escape velocity is huge compared to planets. Matter does not drift away easily. Light still escapes because a white dwarf is not a black hole, but it is held tightly, like a fist closed around mass. And yet, for all that compression, white dwarfs can be among the most quietly stable objects in the galaxy. They simply cool. When a white dwarf is newly formed, it is extremely hot. It glows brightly, often white-blue, which is where the name comes from. But it is no longer generating new energy by fusion. It is cooling like an ember. Over time, it radiates away its stored heat into space. This cooling is slow. A white dwarf has a lot of thermal energy locked into dense matter, and it loses that heat gradually. Astronomers can observe populations of white dwarfs in star clusters and use their cooling rates as a kind of cosmic clock. Older clusters tend to have cooler, dimmer white dwarfs. Younger clusters have hotter, brighter ones. White dwarf cooling models are part of how astrophysicists estimate the ages of stellar populations. This is another way the place where a star dies becomes scientifically valuable. A region of space filled with old stars also tends to be filled with old white dwarfs, and those white dwarfs quietly record the passage of time. There is also a subtle and beautiful detail in how white dwarfs cool. At sufficiently low temperatures, the dense interior can begin to crystallize. The ions, such as carbon and oxygen nuclei, can arrange into a crystalline lattice because the conditions allow them to settle into an ordered structure. This does not mean the white dwarf becomes a glittering gemstone in space, but it does mean the interior can behave more like a solid than a fluid. Cooling can slow as latent heat is released during crystallization, stretching the timeline further. So the white dwarf is a paradox to the untrained eye. It is a stellar remnant that does almost nothing, yet it embodies some of the deepest physics known. Quantum mechanics holds it up. Thermodynamics guides its cooling. Gravity shapes its compactness. And the Chandrasekhar limit defines the boundary beyond which this quiet stability cannot last. All of this answers part of the question of what happens where a star dies. It does not vanish. It does not always explode. Often it leaves behind a dense core supported by quantum rules, sitting in space like a quiet monument to the long life that came before. But there is another lesson in Chandrasekhar's work that hangs in the background like a distant rumble. If electron degeneracy pressure has a limit, then there are stars whose deaths cannot end in this calm way. There are cores too massive to become stable white dwarfs. There are stellar endings where gravity pushes past this quantum resistance and squeezes matter into even stranger states. For now, though, the white dwarf offers a kind of calm clarity. It is the proof that the universe can build an object that is no longer alive as a star, yet still refuses to collapse. A star dies, and in its place remains a dense, slowly cooling ember, held up by the simple fact that electrons cannot all be the same thing in the same place at the same time. The light has changed, the structure has changed, but the region of space is not empty. It is occupied by a remnant that is quiet, compact, and astonishingly real. There comes a point where the gentle endings stop applying. Not because the universe becomes dramatic for entertainment value, but because mass changes the rules. A star that begins its life with many times the sun's mass spends that life under far stronger gravity, at far higher temperatures, and with fusion running at a pace that is almost impatient. It shines brighter, burns hotter, and lives faster. And when its fuel begins to fail, it does not have the option of settling into a quiet, quantum-supported ember, the way a modest star can. In a massive star, gravity is a constant pressure cooker. The core is squeezed so intensely that temperatures climb high enough to unlock new kinds of nuclear fusion, one after another. Hydrogen fusion becomes helium. Helium fusion becomes carbon and oxygen. And then, if the star is massive enough, it keeps going. Carbon can fuse into heavier elements. Oxygen can fuse. Silicon can fuse. Each stage is a step toward heavier and heavier nuclei. This is sometimes described as a star climbing a ladder, but it is less like climbing and more like being pushed. Gravity never stops trying to compress the core. Fusion is the only thing that pushes back. When one fuel becomes scarce, pressure weakens, the core contracts, temperature rises, and the next fuel can ignite. The star evolves by tightening itself into higher temperatures, unlocking more difficult reactions, and spending its remaining time in shorter and shorter bursts. The timescales are part of what makes massive stars feel almost unreal. Hydrogen burning can last millions of years. Helium burning lasts less. Carbon burning lasts less still. Neon burning and oxygen burning are briefer again. silicon burning can be astonishingly short by comparison. The star that once held steady for ages begins to change in a way that is fast, even by astronomical standards. It is still calm in the sense that it follows clear physical laws, but the clock is speeding up. As these stages unfold, the star develops an internal structure that looks like nested layers. The outer layers may still contain hydrogen. Inside that, a shell where hydrogen is burning. Deeper in, a shell where helium is burning. Deeper still, shells where carbon, neon, oxygen, and silicon burn in turn, depending on the star's mass and exact history. This layered arrangement is often called an onion shell structure because each stage of burning forms its own shell around the increasingly dense core. The key point is that these shells are not decorative. They are a consequence of temperature. Each type of fusion requires a higher temperature than the one before it. The hottest region is the center, so the heaviest burning happens deepest. As the core changes composition, burning migrates outward into shells, while the center becomes the ash of the most recent fuel stage. The star becomes a kind of nuclear archaeology site, with each layer recording what has burned and what remains. Eventually, a massive star reaches a kind of dead end, iron. This is not because iron is special in a mystical sense. It is special in a nuclear physics sense. Up to iron, fusing lighter elements into heavier ones generally releases energy. That energy supports the star, providing the outward pressure that fights gravity. But iron sits near the peak of nuclear binding energy per nucleon. In plain terms, iron nuclei are already very tightly bound. Trying to fuse iron into heavier elements does not release energy. It consumes energy. So when the core becomes dominated by iron, fusion stops being a source of support. The star's central engine reaches a point where it cannot generate outward pressure through further fusion. And because gravity never takes breaks, the moment that support fails, collapse begins. At first, the iron core is held up partly by electron degeneracy pressure, the same quantum mechanical effect that supports a white dwarf. But the iron core in a massive star continues to grow, as silicon burning in a surrounding shell keeps producing more iron group elements. The core's mass increases, density increases, gravity tightens. Then another process undermines the remaining support. At the extreme temperatures and densities of a massive star's late core, energetic gamma radiation can break apart iron nuclei. This process is called photodisintegration. It takes energy away because breaking a nucleus apart requires energy input. The star is, in effect, forced to spend its own internal energy tearing apart the very material it built. That removes pressure support even further. At the same time, electrons are pushed into nuclei and combine with protons to form neutrons, releasing neutrinos. This is electron capture. It reduces the number of electrons available to provide electron degeneracy pressure. So the quantum resistance weakens precisely when gravity is becoming strongest. These processes, taken together, trigger a catastrophic inward collapse of the core. The iron core falls inward at a significant fraction of the speed of light. In less time than a calm breath, a region that was once comparable in size to Earth compresses down to something closer to the scale of a city. Matter is squeezed beyond ordinary atomic structure. Electrons are forced into protons. Neutrons begin to dominate. The core becomes a proto-neutron star. And this is where something strange and deeply important happens. The collapse does not simply continue smoothly into oblivion. When the core reaches nuclear densities, the strong nuclear force and neutron degeneracy pressure push back. The inner core stiffens. It rebounds. A shock wave forms and begins moving outward. It sounds at this point like the star should explode cleanly. Shock wave out, star blown apart, story finished. But nature is rarely that tidy. The shock wave loses energy as it travels outward. It spends energy breaking apart heavy nuclei. It spends energy fighting its way through infalling material. In early simulations, the shock often stalled, failing to produce a successful supernova explosion. This was, for a long time, one of the central puzzles of supernova theory. The missing ingredient is tied to one of the most elusive particles in physics, the neutrino. Neutrinos are produced in enormous numbers during core collapse. When electrons combine with protons to form neutrons, neutrinos are released. The proto-neutron star is so hot and dense that it radiates neutrinos of several types in a tremendous burst. In a core collapse supernova, the vast majority of the gravitational energy released during collapse is carried away by neutrinos, not by light. This is an astonishing fact to sit with. A supernova can briefly outshine a galaxy in visible light. Yet even that spectacular brightness is only a thin surface sheen compared to the neutrino flood pouring out of the core. For a brief period, neutrinos interact with the dense matter around the proto-neutron star enough to deposit energy behind the stalled shock. This neutrino heating can revive the shock wave, pushing it outward again and allowing the star's outer layers to be blown into space. This idea, often called the neutrino-driven mechanism, is a cornerstone of modern core collapse supernova modeling. It is also a reminder that even in the most violent stellar deaths, the key processes can be subtle, hidden in particles that barely touch ordinary matter. When the shock successfully erupts outward, the star's outer layers are expelled at thousands of kilometers per second. The envelope tears away. The star becomes a supernova. And where the star dies, space changes dramatically. A supernova does not just remove a star, it injects energy into the surrounding interstellar medium. It drives shock waves through gas clouds. It compresses some regions, potentially triggering new star formation. It heats other regions, preventing collapse for a time. It enriches the galaxy with heavy elements formed during the star's life and during the explosion itself. This is a key difference from quiet deaths. A planetary nebula is an exhale. A core collapse supernova is a rearrangement of the neighborhood. It also leaves behind a remnant. If the core is not too massive, the proto-neutron star cools and settles into a neutron star. If it is more massive, collapse can continue beyond neutron support, forming a black hole. The outcome depends on mass, rotation, and the complex dynamics of the explosion. But in either case, the place where the star died now contains an ultra-compact object, surrounded by expanding debris that glows for centuries. All of that is the theory in broad strokes. But there is a particular event that gave this story a kind of historical anchor, a rare moment when the universe allowed observers to watch a core collapse supernova with multiple kinds of evidence. That event was supernova 1987A. In late February of 1987, a star exploded in the Large Magellanic Cloud, a small neighboring galaxy visible from the southern hemisphere. The supernova became bright enough to be seen with the naked eye. the nearest naked-eye supernova observed since the early 17th century. Astronomers around the world turned telescopes toward it immediately, measuring its light curve, its spectrum, and the expanding debris. But the most extraordinary part came from particles that do not care about telescopes. Several hours before the visible light reached its peak, detectors on Earth recorded a small burst of neutrinos. The Kamiokande 2 detector in Japan, associated with research led by Masatoshi Koshiba's group, detected a cluster of neutrino events. The Irvine, Michigan Brookhaven detector in the United States, known as IMB, also detected neutrinos. The Baksan Neutrino Observatory in the Soviet Union reported detections as well. The number of neutrinos detected was small because neutrinos almost never interact with matter, and the detectors were limited in size. But the timing and energy of those detections were a profound confirmation. They matched the idea that core collapse releases a huge neutrino burst as the core forms a neutron-rich remnant. It was one of the clearest pieces of evidence that the core collapse picture was not just a theoretical story. Something like it truly happens. Supernova 1987. A also revealed how complex the aftermath can be. The expanding debris was not a perfect sphere. Later observations, including those from the Hubble Space Telescope, showed an intricate system of rings around the remnant. These rings were likely shaped by the star's mass loss before the explosion and by interactions between stellar winds at different phases of the star's life. When the supernova blast wave reached these rings, it created bright hotspots, lighting them up like beads around a cosmic hoop. This is another answer to what happens where a star dies. The region becomes an expanding, evolving structure. It is not a single flash and then silence. It is a long-lived interaction between shock waves and pre-existing gas, between newly ejected elements and the material the star shed earlier. The death site becomes a laboratory of plasma physics, radiative cooling, and gas dynamics. And all of it began with the iron core. That is the quiet tragedy inside the massive star's story. The star spends its life building heavier elements because fusion provides stability. But the moment it builds an iron core, the very process that kept it alive becomes impossible. The star cannot fuse iron to gain energy. So gravity takes over completely. The collapse is swift. The rebound is violent. Neutrinos flood outward. The shock wave either fails and leads to direct collapse, or it is revived and tears the star apart. If the explosion succeeds, it leaves a supernova remnant rich in heavy elements. Oxygen, silicon, sulfur, calcium, and iron are scattered into space. Many of the atoms that will later be part of rocks, oceans, and living cells have this kind of origin story. Not because the universe is sentimental, but because nuclear physics and gravity leave few alternatives. The pacing of events in the final moments is almost impossible to picture, and yet it is governed by clear principles. When fusion support ends, collapse is inevitable. When collapse reaches nuclear density, matter pushes back. When the shock stalls, neutrinos can re-energize it. When the outer layers are expelled, the region around the star becomes energized, enriched, and reshaped. So the road to catastrophe is not random. It is structured. It is a chain of causes. Mass leads to hotter cores. Hotter cores allow heavier fusion. Heavier fusion builds an iron core. Iron shuts down energy production. Collapse begins. Neutrinos surge, and the space around the star is transformed. And after the bright flash fades, after the expanding debris grows thinner and cooler, there remains a compact object at the center, still marking the location where the star once balanced gravity with fire. The star is gone. But the place where it died is now one of the most extreme environments the universe can create. After the supernova flash fades, the region where the star died does not become quiet in the way most people imagine. The bright visible light might vanish in weeks or months, and the expanding debris may thin into delicate wisps over centuries, but the core left behind can remain intensely active. It may spin, it may beam, it may crackle with magnetic fields strong enough to rewrite any ordinary idea of matter. This is the domain of the neutron star. A neutron star forms when a massive star's core collapses and is squeezed past the point where electrons can remain as they were. In the crushing final moments, electrons are driven into protons, creating neutrons and releasing neutrinos. The core becomes neutron-rich matter, and it compresses to a density that is almost beyond intuition. At these densities, an ordinary picture of atoms breaks down. There is no longer a structure of nuclei surrounded by electron clouds in the familiar sense. The matter is packed so tightly that the average separation between particles is comparable to the scale of an atomic nucleus. The core becomes a compact object only tens of kilometers across, holding a mass comparable to the Sun or even more. Gravity is still trying to compress it further. The inward pull is enormous, and yet, in many cases, the collapse halts. It halts for the same kind of reason a white dwarf can halt collapse, but at a deeper, harsher level. In a white dwarf, electron degeneracy pressure provides the key resistance. In a neutron star, the primary resistance is neutron degeneracy pressure, along with a strong nuclear force that becomes important when particles are forced extremely close together. Neutron degeneracy pressure arises from the same quantum mechanical principle that governs electrons, the Pauli exclusion principle. Neutrons are fermions, and they cannot all occupy the same quantum state. When gravity tries to compress neutrons into too small a volume, the neutrons resist by being forced into higher and higher energy states. That resistance becomes a pressure that can counter gravity. There is a calm simplicity to this, despite the extremity. The star dies, gravity collapses the core, and quantum mechanics pushes back again. The universe keeps finding ways to build structure out of limits. But the neutron star is not merely a denser white dwarf. It is an entirely different category of object, with its own strange behaviors. And some of the strangest come from two linked properties: rotation and magnetism. When a star collapses into a neutron star, it often spins faster. This is a direct consequence of conservation of angular momentum. If a large rotating object shrinks dramatically in size, its rotation rate increases. The effect is similar to a figure skater pulling in their arms to spin faster. A star's core may have been rotating slowly before collapse. After collapse into a compact neutron star, it can rotate many times per second. At the same time, the star's magnetic field can be amplified. Magnetic field lines are effectively compressed as the core shrinks, strengthening the field. The result can be a neutron star with a magnetic field far stronger than anything that can be produced on Earth. In some cases, these magnetic fields are so strong they influence the behavior of atoms and the structure of matter at the surface. So the place where a star dies can become a compact object that spins rapidly and carries an immense magnetic field. This combination can produce one of the most iconic astronomical phenomena of the 20th century, the pulsar. A pulsar is a rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. If the neutron star's magnetic axis is not perfectly aligned with its rotation axis, the beams sweep through space like a lighthouse. When that beam crosses Earth, radio telescopes detect a pulse, then another, then another. The pulses arrive with astonishing regularity. This is how pulsars were first discovered. In 1967, Jocelyn Bell Burnell, then a graduate student working with Anthony Hewish at the University of Cambridge, noticed a strange signal in radio telescope data. It was a series of regular pulses, repeating with such precision that it was briefly nicknamed "Little Green Men" in private. Not because the researchers truly believed it was extraterrestrial, but because the signal seemed too clean and too consistent to be an ordinary cosmic source. The real answer was more beautiful than any prank from the stars. The signal was the signature of a rotating neutron star. That discovery revealed that the place where a star dies can become an extraordinarily precise natural clock. Pulsars can keep time so reliably that they rival some atomic clocks over certain intervals. Their stability allows scientists to use them as tools, not just objects of curiosity. Pulsar timing can test aspects of physics, map the interstellar medium, and even contribute to the search for low-frequency gravitational waves through pulsar timing arrays. The National Radio Astronomy Observatory, with facilities such as the Green Bank Telescope in West Virginia and the Very Large Array in New Mexico, has been central to pulsar research for decades. Observations from these instruments have helped catalogue pulsars, measure their periods and slowdowns, and study how their radio pulses change as they travel through the ionized gas between stars. One of the key observations is that pulsars gradually slow down. This happens because they lose energy over time, partly through electromagnetic radiation and particle winds driven by their magnetic fields. As they slow, their pulse period increases. Some pulsars spin many times per second, others rotate more slowly. But in general, a pulsar's life is a gradual fading of rotation, a long loss of energy into space. Some neutron stars behave even more dramatically. There are neutron stars called magnetars, which have exceptionally strong magnetic fields. Magnetars can produce powerful X-ray and gamma-ray flares when their magnetic fields twist and reorganize, sometimes cracking the crust of the neutron star in the process. Even without dwelling on the most violent outbursts, the existence of magnetars emphasizes a broader point. A neutron star is a compact object where magnetic energy can rival or exceed other energy reservoirs at the surface. The surface environment of a neutron star is itself extreme. Gravity is so strong that the star's atmosphere, if it has one at all, is incredibly thin. The crust is thought to be a lattice of nuclei under tremendous pressure, with electrons squeezed into dense states. Deeper down, the matter becomes increasingly neutron-rich. In the inner regions, there may be exotic phases of matter, perhaps including superfluid neutrons and superconducting protons. These are active areas of research because the behavior of matter at such densities cannot be fully replicated in laboratories on Earth. Even so, the broad support mechanism is clear. Neutron degeneracy pressure combined with the strong nuclear force can hold up the star against gravity up to a point, and that up to a point matters, because neutron stars also have a maximum mass. If a collapsing core is too massive, neutron degeneracy pressure is not enough, and collapse continues into a black hole. The exact maximum mass depends on the equation of state of dense nuclear matter, which is a way of describing how pressure relates to density in that regime. This is one reason neutron stars are so scientifically valuable. By measuring their masses and radii, astronomers can constrain the physics of matter at nuclear densities. Many neutron stars are found in binary systems. Some pull in gas from a companion star. This accreting material can form an accretion disk and heat up, emitting X-rays. In some systems, accretion can spin up the neutron star, creating what are called millisecond pulsars, which rotate hundreds of times per second. These objects are like recycled neutron stars, spun back up by stealing angular momentum from infalling matter. Again, the place where a star dies does not remain passive. It can become an engine in its own right, powered not by fusion, but by rotation, magnetic fields, and gravity's ability to accelerate matter in intense ways. Neutron stars also leave fingerprints on their surroundings. The particle winds and radiation they emit can inflate nebulae called pulsar wind nebulae, such as the Crab Nebula, which is powered by a central pulsar. The expanding supernova remnant becomes energized by the compact object at its heart. The death site becomes a hybrid structure, debris expanding outward, with a compact rotating core injecting energy and shaping the emission. So when asked what happens where a star dies, one answer is this: the region can become a lighthouse. A neutron star may sit in the center of an expanding supernova remnant, spinning, magnetized, and broadcasting pulses that cross space for thousands of years. Those pulses can be detected across the galaxy. They can be timed. They can be used to probe the space between stars. They can reveal the presence of companions. They can even help test theories of gravity. And the underlying physics is as simple as it is strange. Gravity compresses matter to extreme density. Quantum mechanics resists through the Pauli exclusion principle. The remnant becomes compact. Conservation of angular momentum makes it spin faster. Magnetic field compression strengthens its magnetism. The rotation and magnetism produce beams. The beams become pulses. It is a neat chain of cause and effect, and it turns a dead star into a new kind of cosmic signal. Yet even here in this compact stability there is a quiet tension. A neutron star is a balance, much like an ordinary star, but it is a balance held at far more extreme conditions. Gravity is stronger. Density is higher. The margin of stability is thinner. And beyond that margin lies something even more final. Because if neutron degeneracy pressure has limits, then there are deaths where even neutron stars cannot survive. And in those cases, the place where the star dies becomes something darker than a lighthouse, something defined not by beams of radiation escaping, but by an edge beyond which nothing can return. There is a final kind of stellar ending where even the neutron star's stubborn resistance is not enough. Gravity keeps squeezing, matter keeps compressing. The core's mass is too great for neutron degeneracy pressure and the strong nuclear force to hold it up. The balance breaks. Collapse continues, not just toward higher density, but toward a point where the usual ideas of space and time begin to behave in unfamiliar ways. This is where black holes enter the story. A black hole is often described as a cosmic vacuum cleaner, an object that sucks in everything nearby. But that picture is misleading. A black hole is not a special kind of pulling. It is gravity behaving exactly as gravity always does, but concentrated into a region so compact that the escape speed exceeds the speed of light. In other words, it is not that a black hole has a different kind of gravity. It is that the same gravity has been compressed into a smaller space. To make sense of that statement, the universe needs a different language than ordinary gravity. Isaac Newton's gravity is useful for planets and most stars, but it treats gravity as a force acting across space. In the early 20th century, Albert Einstein introduced a deeper description: general relativity. In general relativity, gravity is not a force in the usual sense. Gravity is the curvature of spacetime caused by mass and energy. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. That idea sounds abstract, but it becomes almost unavoidable when describing black holes, because black holes are not just dense objects. They are regions where space-time curvature becomes extreme. Shortly after Einstein published the field equations of general relativity, Carl Schwarzschild found a solution describing the space-time around a simple, non-rotating, spherically symmetric mass. Schwarzschild did this while serving in the First World War, which adds a strange historical quietness to the fact that the mathematics of one of nature's most extreme objects was worked out amid ordinary human catastrophe. Schwarzschild's solution revealed something startling. If a mass is compressed within a certain radius, the structure of space-time changes in a fundamental way. That radius is now called the Schwarzschild radius. It is the radius of the event horizon for a non-rotating black hole. The event horizon is not a physical surface. It is not a shell of hard material. It is a boundary in space-time. It marks the point beyond which no signal can reach the outside universe, because the paths that light can take no longer lead outward. Past this boundary, all future directed paths point deeper inward. This is the calm truth behind the drama. A black hole is defined by an edge where escape becomes impossible. The Schwarzschild radius depends on mass. The more massive the object, the larger the radius. For a mass comparable to the Sun, the Schwarzschild radius is only a few kilometers. That is one of the most unsettling facts about stellar mass black holes. Compress the Sun down to a sphere only a few kilometers in radius, and it becomes a black hole. Not because it has been given a new property, but because space-time curvature has reached a threshold where light cannot get out. So when a massive star dies and its core collapses, if the core's mass is high enough, it can be compressed within its Schwarzschild radius. At that moment, an event horizon forms. And from the perspective of the outside universe, the star's core has become a black hole. This also answers part of the question of what happens where a star dies. The region does not become empty. It becomes defined by a boundary that cannot be crossed outward. The star's light is gone, but its gravitational influence remains. Planets, gas clouds, companion stars, and passing material still feel the gravity of the mass that collapsed. In many ways, at large distances, a black hole behaves like any other object of the same mass. If the Sun were replaced by a black hole of the same mass, Earth's orbit would remain nearly the same, at least in terms of basic gravitational mechanics. The difference is not in how it pulls from far away, but in what happens very close to it. Near a black hole, space-time curvature becomes strong. Time behaves differently relative to distant observers. Paths of light bend dramatically. The gravitational field becomes tidal, meaning it can stretch and compress objects along different directions. Close enough, those tidal forces can become destructive, pulling an object apart. The event horizon itself is often misunderstood as a place where something dramatic happens, like a wall of fire or a crushing barrier. In general relativity, for a sufficiently large black hole and a sufficiently small object falling freely, crossing the event horizon can be uneventful in the local sense. There is no sudden flash that announces, in the falling object's own frame, that a boundary has been crossed. The boundary is defined by the geometry of space-time, not by a physical surface. The drama arises from the consequences. Once inside, return is impossible. Even light cannot climb back out, not because light is tired, but because there are no outward directed paths left. This is why black holes are so important to a story about where a star dies. The place becomes an absence that is also a presence, a region that cannot send information outward, yet can influence the universe through gravity. But how can something that does not emit light be studied? For most of the 20th century, black holes were inferred rather than seen. Astronomers observed X-ray binaries where invisible compact objects pulled gas from companion stars. The gas formed accretion disks, heated up, and emitted X-rays. By measuring orbital motion and mass estimates, astronomers could conclude that the unseen object was too massive and too compact to be a neutron star. Black hole candidates accumulated. Still, there was a lingering sense that black holes were mathematical, almost philosophical, until the universe began offering more direct evidence. One of the most striking pieces of modern evidence comes from the Event Horizon Telescope. The Event Horizon Telescope is not a single instrument. It is a global collaboration that links radio observatories across Earth using a technique called very long baseline interferometry. By combining signals from many telescopes spread across the planet, the collaboration effectively creates a virtual telescope roughly the size of Earth. That immense baseline provides enough resolution to observe structures on the scale of an event horizon for nearby supermassive black holes. When the Event Horizon Telescope released the first image of a black hole shadow, it was an extraordinary moment. The image showed a bright ring of emission surrounding a darker central region. The bright ring comes from hot gas in the accretion flow, with light bent by gravity. The darker region is not the black hole itself as a body, but the shadow, the silhouette, created by light, being captured by the event horizon and by extreme gravitational lensing. Later, the Event Horizon Telescope produced an image of the supermassive black hole at the center of our own galaxy, Sagittarius A star. The data analysis was complex because Sagittarius A star changes rapidly, but the resulting image again showed a ring-like structure consistent with the predictions of general relativity. These images matter because they connect theory to observation. Schwarzschild's mathematical solution, Einstein's description of gravity as curved spacetime, and the concept of the event horizon are no longer only equations on paper. They are tied to real data collected from real instruments, looking at real objects. And yet, the story of stellar mass black holes, the ones made from dying stars, has its own quieter implication. If black holes form from collapsed stellar cores, then the galaxy likely contains many of them. Most are dark and undetectable unless they are actively accreting material or interacting with a companion. The Milky Way could be filled with black holes that drift silently through the disk and halo, gravitationally present but visually invisible. So the place where a star dies can, in some cases, become a dark gravitational well, defined by an event horizon. What remains around that well depends on the environment. If the star had outer layers blown off in a supernova, those layers expand away, enriching space. If the collapse happens with little explosion, some material may fall back inward, forming an accretion disk. In binary systems, a companion star can feed gas into the black hole's gravitational field, creating luminous accretion disks and relativistic jets. In those cases, black holes are not quiet at all. They can be among the brightest sources in the sky, not because the black hole emits light, but because matter falling toward it releases enormous energy before crossing the horizon. This is another subtlety that is worth stating plainly. A black hole is dark, but the region around a feeding black hole can be dazzling. The light comes from friction, heating, and magnetic processes in the accretion flow. The energy source is gravitational potential energy converted into heat and radiation as matter spirals inward. In general relativity terms, the deeper matter falls into the curved space-time well, the more energy can be released. Accretion onto compact objects can be extremely efficient. It can convert a significant fraction of infalling mass into radiant energy before the material disappears past the horizon. That is why black holes can power quasars and active galactic nuclei when fed at large scales. But even on the smaller scale of stellar mass black holes, accretion can produce intense X-ray emission and jets. So black holes are not merely endings. They are boundary objects where physics crosses into regimes that challenge intuition. They are also engines in the sense that they can convert gravitational infall into radiation more efficiently than many other processes. Still, in the context of stellar death, the black hole represents a final state where the star's core has collapsed past all known material supports. Electron degeneracy pressure fails at high enough mass. Neutron degeneracy pressure fails at higher mass still. Beyond that, gravity creates an event horizon. This is why black holes demand narrative space. They change the question from what matter becomes to what space-time becomes. A white dwarf is a star's core supported by electrons obeying the Pauli exclusion principle. A neutron star is a core supported by neutrons and the strong nuclear force. A black hole is a core where the collapse has gone so far that the outward paths of light have been erased by curvature. And yet, even in this final darkness, the place where the star died continues to matter. The black hole carries the star's mass forward into the future. It can interact gravitationally with its environment. It can merge with other compact objects. It can shape the motion of nearby stars. It can, in binary systems, reveal itself through accretion and X-rays. It can, in mergers, send gravitational waves across the universe, ripples in space-time itself. A star dies. And in some cases, the space where it once burned becomes defined not by what can be seen, but by what cannot escape. When a star dies, it does not only change the space it occupied, it changes the chemistry of the galaxy. That sounds poetic, but it is also literal. The elements that make up rocks, oceans, atmospheres, and the complicated carbon-rich molecules used by life do not appear fully formed at the beginning of the universe. The early universe was mostly hydrogen and helium with tiny traces of lithium. Almost everything heavier had to be manufactured later, inside stars, and in the violent aftermath of stars that could no longer hold themselves together. A star is a furnace that runs for a long time. During most of its life, it turns hydrogen into helium. In later stages, some stars can fuse helium into carbon and carbon into heavier elements, building an internal inventory that did not exist when the star was born. But there is a limit to what slow, steady fusion can do. Some of the most valuable elements in the periodic table, especially the very heavy ones, require conditions far more extreme than the gentle pressure of an ordinary stellar core. This is where the story of heavy elements becomes inseparable from stellar death. When a massive star explodes as a core collapse supernova, the explosion is not only an act of destruction, it is also an act of creation. The shock wave and the intense heat can drive nucleosynthesis, forging new isotopes and dispersing them outward. The expanding debris carries oxygen, silicon, sulfur, calcium, iron, and many other products into the interstellar medium. Over time, those atoms mix into the gas between stars. That enriched gas later collapses to form new stars and planets, and the chemical richness of a galaxy slowly increases. In this sense, a supernova is a kind of galactic fertilizer event. It is one of the ways a galaxy gradually upgrades itself from a simple mix of light elements to a chemically diverse ecosystem. But even supernovae cannot easily account for everything. Some of the heaviest elements, including gold, platinum, and uranium, are strongly linked to a process that requires extraordinary neutron densities. This is called the R process, short for Rapid Neutron Capture Process. The R process is a way of building heavy nuclei quickly by bombarding seed nuclei with neutrons so rapidly that the nuclei capture neutrons faster than they can decay. The nuclei grow heavier and heavier, stepping through unstable forms, and then later decay into more stable heavy elements. It is an efficient method for assembling the far end of the periodic table, but it demands an environment flooded with free neutrons. For a long time, the exact cosmic birthplace of the R process was debated. Core collapse supernovae were once considered the main candidate, and some supernova environments may contribute under certain conditions. But a second site has emerged as especially important and, in many cases, dominant for producing a large fraction of R process elements: neutron-star mergers. A neutron-star merger begins with a binary system. Two massive stars live, die, and leave behind two neutron stars orbiting each other. Over long spans of time, their orbit shrinks. The system loses orbital energy through gravitational waves, a prediction of general relativity that has become a measurable reality. As the orbit tightens, the neutron stars spiral inward faster and faster until they collide. This collision is an event of staggering density and complexity. Neutron-rich matter is flung outward. Temperatures soar, magnetic fields twist. Space is flooded with neutrons. It is precisely the kind of environment the R process thrives in. In the aftermath, some of the ejected neutron-rich material undergoes rapid neutron capture, forming heavy nuclei that later decay. The decaying material powers an electromagnetic glow called a kilonova, a transient event that can shine across optical and infrared wavelengths. In those days and weeks after the merger, The universe is effectively advertising its element-making machinery. This is not just theory. Observations have linked neutron star mergers to kilonova signatures and to the production of R-process elements. The broader idea is now widely integrated into how astrophysicists model chemical evolution in galaxies. Stars build and release many elements. Supernovae enrich space further, and neutron star mergers provide a powerful channel for the heaviest R-process materials. So the place where a star dies can echo far beyond the original location. The elements thrown into space do not stay put. They drift, mix, collapse into new clouds, and become part of new systems. A star can die in one corner of a spiral arm, and the material from its death can later appear in a planet forming in another region entirely. That is one of the strangest comforts in astrophysics. Stellar death is not only subtraction, it is redistribution. Over time, this redistribution builds what could be called the chemical personality of a galaxy. Some galaxies remain relatively chemically primitive, especially small galaxies that lose enriched gas easily. Larger galaxies, especially those with long histories of star formation, tend to accumulate heavier elements more effectively. The Milky Way, with its long and eventful history, is a chemically diverse place. And this chemical diversity shapes everything from planet formation to the kinds of stars that can form next. Metals, in astronomical language, means any element heavier than helium. A galaxy with more metals can cool gas clouds more efficiently, because heavier atoms and molecules can radiate energy away in ways that pure hydrogen and helium cannot. Efficient cooling allows gas to collapse into denser structures. It also supports the formation of dust grains, which become the seeds for building rocky planets. So the aftermath of stellar death changes the next generation's possibilities. It changes what kinds of planets can exist and what materials can be assembled. This is why looking at stellar death is not only about endings. It is about the long-term evolution of galaxies. This wider perspective becomes even clearer when the focus shifts from a single death event to the accumulated results of billions of deaths over cosmic time. Galaxies are not just collections of shining stars. They are also collections of remnants, leftovers, and quiet objects that no longer burn in the ordinary way. A mature galaxy is, in part, a stellar graveyard. White dwarfs are everywhere in older stellar populations. Each one is the compressed core of a modest star, supported by electron degeneracy pressure, cooling slowly over time. Neutron stars are rarer but still significant, especially in regions with a long history of massive star formation. Black holes, too, may be scattered throughout a galaxy, often invisible unless they are feeding. These remnants are not passive. They interact gravitationally with the galaxy. They can heat stellar systems through gravitational encounters. They can merge, releasing gravitational waves and, in some cases, producing electromagnetic afterglows. They can influence the dynamics of star clusters and the evolution of binaries. They are part of the galaxy's ongoing story, even if they emit little light. When astronomers talk about a galaxy's stellar population, they often divide it into broad categories associated with age and history. Some regions have ongoing star formation rich in young, massive, luminous stars. Other regions are dominated by older stars, where star formation has slowed or stopped, leaving behind a quieter population with more remnants and long-lived low-mass stars. This is one reason galaxies can look so different depending on their age and environment. Spiral galaxies often show bright star-forming arms, while elliptical galaxies tend to be dominated by older stars and have little cold gas left for new star formation. In such older systems, the visible light is often dominated by long-lived stars, but the invisible mass includes many remnants that do not shine brightly. Modern observations help map this long arc of galactic evolution. The James Webb Space Telescope has provided deep infrared views that reveal distant galaxies at very early times in the universe, when star formation rates were higher and galaxies were rapidly assembling. Infrared capability matters because light from very distant galaxies is redshifted by cosmic expansion. The James Webb Space Telescope can see this shifted light, allowing astronomers to study early star formation, early chemical enrichment, and the emergence of structure. These observations help connect stellar death to cosmic history. In the early universe, massive stars formed quickly and died quickly, enriching their surroundings early. As time passed, chemical enrichment built up, changing how gas cooled and how subsequent generations of stars formed. The universe moved from a simpler chemical state toward a more complex one. In this larger view, the place where a star dies is not merely a point on a map. It is a node in a vast network of cause and effect. Death creates debris. Debris enriches gas. Enriched gas forms new stars and planets. Remnants accumulate. Mergers occur. Energy and elements are redistributed again. The galaxy evolves. There is also a striking difference in how visible and invisible these processes can be. A supernova is obvious. It can outshine a galaxy briefly. A planetary nebula glows in colorful shells. A pulsar can pulse loudly in radio waves. But much of the chemical work happens quietly afterward, as debris mixes and cools, as atoms settle into dust grains, as clouds slowly collapse. Even neutron star mergers, dramatic as they are rare compared to supernovae. Their chemical influence can be disproportionate because the R process yield per event can be large. A galaxy might experience relatively few neutron star mergers compared to the number of supernovae, but still acquire a substantial fraction of its heaviest elements from those mergers. This is one reason the chemical evolution of galaxies can vary. The timing and frequency of different death events matters. If neutron star mergers take time to occur, because binaries need time to inspiral through gravitational wave emission, then the appearance of certain heavy elements in early generations of stars can help constrain those timescales. By studying the chemical fingerprints in old stars, astronomers can infer how quickly different enrichment channels began contributing. So stellar death leaves traces not only in space, but in the composition of stars that form later. A star's atmosphere can preserve the chemical signature of the gas cloud it formed from. In that sense, stars can act as fossils of galactic chemical history. They carry within their spectra the story of what kinds of deaths happened before they were born. That story can include supernovae, which enrich the medium with many elements, and neutron star mergers, which deliver R process material in a way that stands out in abundance patterns. The patterns can be subtle, but they are measurable. They turn stellar chemistry into a record of past catastrophe and transformation. All of this widens the meaning of the original question. When a star dies, what happens where it dies depends on the type of death. A planetary nebula paints the region with a soft shell of ionized gas. A supernova slams a shockwave into surrounding space and seeds the medium with heavy elements. A neutron star or black hole remains, carrying mass forward and shaping local gravity. But beyond the local region, the aftermath can travel. It can become part of a galactic ecology, one in which matter is recycled through generations of stars, gradually enriched, gradually rearranged, and gradually assembled into more complex structures. It can become part of new worlds. It can become the iron in a planet's core, the oxygen in its rocks, the gold in its crust, the carbon in its chemistry. A star dies in one place, and the consequences carried by expanding gas and time can show up almost anywhere else. In the end, a galaxy is not only a collection of stars, it is a collection of endings layered over time, each one leaving behind matter, remnants, and subtle chemical changes that alter what the galaxy can become next. A star can die alone, quietly shedding its outer layers into space. It can die violently, collapsing and exploding in a core collapse supernova. But there is another path that is neither purely gentle nor purely solitary, a path where death is shaped by companionship. In many parts of the galaxy, stars are not single. They are born in pairs or in larger multiple systems bound together by gravity. They orbit a shared center of mass, and over time their lives become entangled. In these systems, stellar death is not always an internal decision made by a core running out of fuel. Sometimes it is forced. Sometimes it is triggered. Sometimes it is accelerated by a partner that refuses to mind its own business. Binary systems are one of the main reasons the place where a star dies can become unexpectedly energetic long after the star's main fusion life is over. Consider a white dwarf in a binary system. On its own, a white dwarf is a cooling ember, supported by electron degeneracy pressure, radiating away stored heat. But if it orbits a companion star closely enough, it can begin to steal material. Gas from the companion can flow towards the white dwarf through a gravitational pathway, often through a point called the inner Lagrange point. The gas does not fall straight in. It carries angular momentum, so it forms a swirling disk around the white dwarf. This is an accretion disk. An accretion disk is one of the most efficient ways the universe converts gravity into light. As gas spirals inward, friction and turbulence heat it. Magnetic fields can amplify and stir the flow. The inner regions can reach temperatures hot enough to emit X-rays. The disk becomes luminous not because the white dwarf itself is producing fusion, but because the infalling material is releasing gravitational potential energy as it descends into the compact object's gravitational well. This is why some dying star environments are bright in X-rays. The light is not coming from the remnant as a passive object. It is coming from the process of feeding. The Chandra X-ray Observatory has been one of the key instruments for studying these systems. Chandra's sharp X-ray vision has revealed accreting compact objects in our galaxy and beyond, including white dwarfs, neutron stars, and black holes in binary systems. It can resolve X-ray sources in crowded regions like star clusters and galactic centers, helping astronomers identify the energetic leftovers of stellar evolution. In the case of a white dwarf accreting from a companion, the outcome depends on the rate of accretion and the behavior of the accumulating material. If hydrogen-rich gas piles onto the surface, it can ignite in a runaway surface fusion event, producing a nova. A nova is not the destruction of the white dwarf. It is a surface outburst, a brief brightening caused by explosive hydrogen fusion on the surface. The white dwarf remains and the process can repeat. But there is another outcome that is far more final, and it answers the question of what happens where a star dies in a particularly dramatic way. If the white dwarf gains enough mass, it can approach the Chandra X-ray limit. As that limit is approached, electron degeneracy pressure can no longer support the core against gravity. The white dwarf becomes unstable. Carbon and oxygen in the core can ignite under degenerate conditions, leading to a thermonuclear runaway that disrupts the entire star. This is a Type 1a supernova. Type 1a supernova are different from core collapse supernovae. In a core collapse supernova, a massive star's iron core collapses under gravity and rebounds, with neutrinos playing a central role. In a Type 1a supernova, the white dwarf is destroyed by runaway thermonuclear burning. There is no surviving white dwarf core at the center. The compact remnant is effectively erased, replaced by expanding debris rich in iron group elements. That destruction is important for two reasons. First, it provides one of the universe's most reliable standardizable candles. Because Type 1 supernovae involve white dwarfs reaching similar conditions near the Chandra X-ray limit, their peak brightness tends to be comparable, with corrections. This has allowed astronomers to use them to measure cosmic distances and to discover the accelerated expansion of the universe, a result linked to the concept of dark energy. Second, it means the place where a star dies in a Type 1a event becomes a chemical injection point, spreading large amounts of iron and other elements into space. Type 1a supernovae are major contributors to the iron content of galaxies. They help explain why iron becomes abundant in later generations of stars. There is still active research into the exact pathways that create Type 1a supernovae. Some may involve a white dwarf accreting from a normal companion star. Others may involve two white dwarfs merging, known as the double degenerate scenario. In either case, the core idea remains. Binary interaction can turn a quiet remnant into an explosive event. So binary chaos can reawaken the dead. But binaries can also produce some of the most extreme and brief events in the universe, especially when massive stars and compact remnants are involved. When a massive star dies, it can leave behind a neutron star or a black hole. If that remnant has a companion star, accretion can begin. Gas from the companion can form an accretion disk around the neutron star or black hole, heating and emitting X-rays. These X-ray binaries are a major focus of high-energy astronomy. Chandra has observed many such systems, mapping their positions and variability. In some cases, the behavior is steady. In other cases, it is eruptive. Accretion can be unstable, leading to bursts and flares as the disk's flow changes. The environment around the compact object can become a dynamic laboratory of plasma physics, magnetic reconnection, and relativistic motion. When the compact object is a black hole, accretion can produce jets, narrow beams of particles, and energy launched away from the disk at speeds close to the speed of light. These are relativistic jets. They are guided by magnetic fields and powered by the gravitational energy of infalling matter, and possibly by the rotation of the black hole itself. Jets are another way the place where a star dies becomes influential. A jet can punch through surrounding gas, heating it, compressing it, and altering the environment over distances far larger than the compact object itself. Even a stellar mass black hole in our galaxy, in a system called a microquasar, can produce jets that make it a bright, variable source across multiple wavelengths. And then there are the most extreme jets of all, associated with gamma-ray bursts. Gamma-ray bursts are brief flashes of gamma radiation, the highest energy form of electromagnetic radiation. They can last fractions of a second or many seconds, and they can be detected from billions of light-years away. For a few moments, a gamma-ray burst can release an enormous amount of energy, often linked to the collapse of a massive star or to the merger of compact objects. There are two major categories. Short gamma-ray bursts are strongly linked to neutron-star mergers, where the collision produces a relativistic jet and a killer nova. Long gamma-ray bursts are linked to the deaths of massive stars, in a scenario often called the collapsar model. In the collapsar picture, a rapidly rotating massive star collapses into a black hole, and an accretion disk forms around it. That disk powers jets that punch through the star's outer layers. When the jets break out, they produce the gamma-ray burst. This is a different kind of stellar death environment from a typical supernova remnant. It is not simply debris expanding outward. It is a focused, directional event where energy is funneled into narrow beams. If Earth happens to lie along the path of the beam, the burst is detected. If not, it may be invisible in gamma rays, though the aftermath can still be observed at longer wavelengths as an afterglow. The Swift Observatory, operated by NASA, has been crucial in detecting gamma-ray bursts and rapidly pointing other instruments toward them. Swift can detect the initial gamma flash and then slew quickly to observe the afterglow in X-rays and ultraviolet and optical wavelengths. This rapid response has helped map the locations of bursts, identify their host galaxies, and connect them to supernovae or mergers, depending on the type. So again, the place where a star dies becomes more than a point in space. It becomes an event that can be traced across the universe. A long gamma-ray burst ties the death of a massive star to a black hole forming at its center, and a jet drilling outward. A short gamma-ray burst ties the merger of neutron stars to the ejection of neutron-rich matter and the formation of heavy elements through the R process. Both are ways the universe produces extreme energy in brief moments, and both are linked to compact objects, accretion disks, and relativistic jets. It is tempting to treat these as separate stories, but they share a common framework. Compact objects create deep gravitational wells. Infalling matter forms accretion disks. Accretion disks can launch jets. Jets can produce high-energy radiation. Binary companions can provide the fuel, and the deaths of stars provide the compact objects in the first place. This is the chain that makes binaries so powerful in shaping stellar death environments. A star dies. It leaves a remnant. The remnant enters a new relationship with a companion. Material moves. Energy is released. The death site becomes active again, sometimes explosively. And there is a strange symmetry here. In the quiet endings, the star releases its outer layers gently, and a white dwarf cools. In the violent endings, the star collapses and explodes, leaving a neutron star or black hole. In binary endings, the remnant can be re-fed, reignited, and driven beyond its own stability, producing Type 1 a supernovae, X-ray emission, and in some cases jets that broadcast the death across the cosmos in gamma rays. So the universe offers many ways to answer the same basic question. What happens where a star dies depends on mass, yes. But it also depends on companionship. A star does not always get to die on its own terms. Sometimes a partner star keeps the story going, dragging the remnant back into the spotlight, feeding it, spinning it up, pushing it toward a final threshold, and turning what should have been a slow fade into a second, brighter ending. And once those high-energy events pass, once the outbursts fade and the jets weaken, the galaxy is still left with the long-term consequences. New elements, heated gas, expanding shells, and compact objects that continue to drift through the Milky Way, quietly marking the places where stars ended, and sometimes where the aftermath became louder than the life that came before. After the bright endings and the loud aftermaths, there is a quieter truth that settles over almost every stellar death. Remnants endure. They do not keep burning like ordinary stars, but they remain as long-lived punctuation marks in the galaxy, carrying mass forward, shaping nearby motion through gravity, and slowly changing on timescales that make human history feel like a flicker. A white dwarf is one of the calmest examples. At the moment it is born, it can be intensely hot, glowing white-blue as it radiates stored thermal energy into space. But there is no new fuel cycle to keep it warm. No steady nuclear engine. The white dwarf cools the way a hot stone cools after being removed from a fire, except the stone is Earth-sized, dense beyond intuition, and cooling into a universe that grows colder and emptier with time. This cooling is gradual and dependable. At first, a young white dwarf loses heat relatively quickly, shining visibly. Over time, as it cools, it becomes dimmer, redder, and harder to detect. The process can last for billions of years, and then far beyond. The galaxy is old enough that many white dwarfs have already cooled substantially, becoming faint embers that need careful surveys and sensitive instruments to find. In the far future, theoretical models predict a stage even quieter than that. A white dwarf that has cooled so much that it no longer emits significant visible light is sometimes called a black dwarf. It is not black in the sense of being a black hole. It is simply dark, an object that has radiated away most of its stored heat. The phrase is a reminder of scale more than a claim about what can be observed today, because the universe has not existed long enough for true black dwarfs to have formed in large numbers. The cooling times involved stretch far beyond the current age of the cosmos. Even before that deep future is reached, the internal physics of white dwarfs continues to do subtle work. As they cool, many are expected to crystallize in their interiors, with carbon and oxygen nuclei settling into more ordered arrangements. This does not turn them into glittering gems, but it does change how they release heat and how their cooling proceeds. It is one more way stellar death leaves behind objects that are not static lumps, but evolving systems, still governed by thermodynamics and quantum behavior long after fusion has ended. Neutron stars, meanwhile, follow a different kind of slow decline. They are born hot and turbulent, often spinning rapidly and carrying magnetic fields that can be breathtakingly strong. Some announce their presence as pulsars, sweeping beams of radiation through space with clock-like regularity. Others are quieter, or only briefly active. But almost all neutron stars, over time, lose rotational energy. Their spin slows. Their pulses, if they produce them, drift farther apart. This spin down is not mysterious in principle. A rotating magnetized neutron star can radiate energy away as electromagnetic waves, and it can drive a wind of charged particles through its magnetosphere. Both processes drain rotational energy. The neutron star's rotation rate decreases steadily, sometimes smoothly, sometimes with sudden irregularities. Those irregularities can be fascinating. Some pulsars experience glitches, abrupt changes in rotation rate that suggest complex internal structure such as superfluid layers in the interior that can exchange angular momentum with the crust. In these moments, the remnant reveals that it is not a simple, rigid sphere. It is a layered object with exotic states of matter, still capable of surprises. Over much longer timescales, the magnetic field of a neutron star may also decay or reorganize. Magnetars, the most strongly magnetized neutron stars, can release energy through powerful flares when magnetic stresses shift and the crust fractures. But even without focusing on rare flares, the broad pattern remains. Neutron stars gradually become less energetic and less conspicuous. They cool, they slow, they become harder to notice unless something disturbs them, such as accretion from a companion. And then there are black holes, the most austere of remnants. A black hole does not cool in the usual sense because it does not have a surface that radiates stored thermal energy the way a white dwarf does. It does not spin down by radiating beams the way a pulsar does, unless it is interacting with surrounding matter through accretion and jets. Left alone, a black hole can seem like the ultimate quiet survivor. Mass compressed behind an event horizon, gravitationally present, visually absent. Yet even black holes are not necessarily eternal in the deepest sense. This is where one of the most subtle and famous ideas in modern physics enters: Hawking radiation, proposed by Stephen Hawking in the 1970s. The idea arises from combining quantum field theory with a curved spacetime near an event horizon. In that picture, black holes are not perfectly black. They can emit a faint thermal radiation. If they emit radiation, they lose energy. If they lose energy, they lose mass. Over extremely long timescales, a black hole could slowly evaporate. The timescales here are so vast they are almost difficult to hold in the mind. For stellar mass black holes, the evaporation time predicted by Hawking's calculation is enormously longer than the current age of the universe. It is deep future physics, not a near-term astronomical event. Still, the concept matters, because it suggests that even the darkest, most final-seeming remnants might have an ending, not through collapse, but through gradual loss. In a sense, the long-term fate of remnants is a shift from violent astrophysics to patient bookkeeping. Energy leaks away, rotation slows, heat diffuses outward. The universe, through the laws of thermodynamics, keeps nudging systems toward lower available energy. This long view also changes what it means to observe stellar death. A supernova is obvious. A planetary nebula is visible. A pulsar can be detected by its pulses. But some remnants announce themselves in quieter ways, especially through gravity rather than light. Gravity, after all, does not fade when a star dies. Mass remains. Curvature remains. Orbits remain, and when compact objects move and interact, gravity can carry information outward in a form that does not require light at all. This is where modern astronomy has gained a new sense: gravitational wave detection. Gravitational waves are ripples in space-time predicted by general relativity. They are produced when massive objects accelerate in asymmetric ways, especially when compact objects orbit each other and spiral inward. Binary black holes, binary neutron stars, and neutron star black hole pairs can all generate gravitational waves strong enough in the final moments of merger to be detected across vast distances. The LIGO and Virgo collaborations have made this real. By measuring tiny changes in distance across long interferometer arms, these detectors have observed gravitational wave signals from merging compact objects. These detections are not just confirmations of theory. They are direct evidence that stellar death sites do not remain isolated. Remnants can find partners. They can inspiral. They can collide. And when they do, the universe can ring. Some mergers appear as black hole systems, producing gravitational waves but little or no electromagnetic light. Others involve neutron stars, which can produce both gravitational waves and luminous counterparts. A neutron star merger can eject neutron-rich matter and produce a kilonova glow, linking gravitational wave astronomy to the chemical story of our process element formation. This is a new kind of map of where stars die. Not a map made purely of visible remnants, but a map made of mass and motion, detected through space-time itself. There is a quiet elegance to that. For most of human history, astronomy meant light. Eyes, lenses, mirrors, radio dishes. Now the universe can also be listened to through gravity, through the rhythm of merging remnants that were forged in stellar catastrophes long ago. And while LIGO and Virgo listen to mergers in the final seconds, other observatories are preparing to watch the sky for the slower, steadier signatures of stellar death and its aftermath, especially through large-scale surveys. One of the most important upcoming facilities for this kind of work is the Vera C Rubin Observatory. Its wide-field survey, designed to image large portions of the sky repeatedly, will be exceptionally good at finding transient events and changes over time. That includes supernovae, variable stars, tidal disruption events, and the subtle flickers that can reveal compact objects interacting with companions. In practical terms, repeated imaging means a new kind of awareness. Instead of taking a single portrait of the sky, the observatory will take a continuous sequence, building a time-lapse of the universe's changes. That is particularly valuable for stellar death, because so many of its signatures are time-dependent. Explosions brightening and fading, remnants expanding, accretion disks flaring, binaries dimming and brightening, and new transients appearing unexpectedly. This is another way the long-term fate of remnants connects to modern observation. Remnants are not only the endpoints of stellar lives. They are ongoing actors. They produce signals, sometimes subtle, sometimes dramatic, and increasingly, those signals can be captured systematically. In the long view, this is what the galaxy becomes: a mixed population of shining stars and quiet remnants, all moving through a gravitational architecture that holds them together. Some regions are lively with new star formation and frequent supernovae. Other regions are older, calmer, rich in white dwarfs and long-lived low-mass stars. Across the whole system, the remnants accumulate like an archaeological layer, a record of what has already ended. And the deepest time perspective adds an additional layer of calm strangeness. If star formation eventually slows, as galaxies consume or lose their cold gas, then new stars become rarer. The bright, blue, short-lived stars disappear first, leaving longer-lived stars to dominate. The galaxy gradually reddens. White dwarfs become more common. Neutron stars and black holes persist, quiet and compact. Over far longer spans, white dwarfs continue cooling toward black dwarfs. Neutron stars continue spinning down, becoming less active. Black holes in the Hawking picture begin an evaporation so slow that the universe itself may transform many times over before the process completes. This is not a switch-off moment. It is a fade stretched into deep time. And yet, the tools of modern astronomy keep the present moment unusually rich. Gravitational wave detectors can capture the final spiral and merger of objects born in ancient stellar deaths. X-ray observatories can watch accretion flare around compact remnants. Wide-field surveys can catch new supernovae at the moment they bloom. Deep optical and infrared telescopes can inventory the faint populations of remnants and trace how they are distributed through galaxies. So the place where a star dies is not only a dramatic event site. It can become a long-lived object that continues to change, continues to interact, and continues to produce measurable effects, sometimes for billions of years. In the end, stellar death is not only about what disappears, it is about what remains. A cooling ember the size of a planet, held up by quantum rules. A spinning neutron core that ticks out pulses until its rotation finally slows. A black hole that carries mass forward behind an event horizon, occasionally announcing itself through accretion, mergers, or ripples in spacetime. And above all, a galaxy shaped not only by starlight, but by the quiet persistence of stellar remnants, lingering in the dark and making the universe's endings last far longer than its beginnings ever did. By the time the last light of a dying star has faded, by the time its outer layers have drifted away or its supernova debris has thinned into the wider galaxy, the question remains in a strangely simple form. What happens where a star dies? The answer is not one thing. It is a set of outcomes, each one shaped by the same fundamental laws, each one leaving behind a different kind of remnant, a different kind of environment, a different kind of silence. A star begins as a compromise. Gravity gathers matter and tries to crush it inward. Nuclear fusion, ignited by that crushing, releases energy that pushes outward. For most of its life, the star lives inside hydrostatic equilibrium, a balance between inward pull and outward pressure. It shines because that balance holds, and it changes because fuel is not infinite. When the fuel that supports the star's core begins to run out, gravity reasserts itself. It compresses, it heats, it drives the star into new stages, or towards collapse. That is the moment the story shifts from life to death. Not because the star suddenly stops, but because it begins to transform into something fusion cannot sustain. In the gentler endings, the transformation is slow enough that the star can shed its outer layers without being torn apart. A medium-mass star swells into a red giant, rearranges its burning into shells, and eventually releases its envelope into space. That released gas can become a planetary nebula, a glowing shell lit by ultraviolet radiation from the exposed core. The region around the star becomes a soft, expanding cloud, chemically enriched and briefly luminous. At the center, the remnant is a white dwarf. A white dwarf is a stellar core that has found a new kind of support. Fusion is gone. Thermal pressure is no longer the main defense against gravity. Instead, electron degeneracy pressure holds the object up, a consequence of the Pauli exclusion principle. Identical electrons cannot be forced into the same quantum state, so as gravity compresses the core, the electrons resist by occupying higher energy states. That resistance becomes pressure. The white dwarf remains stable, at least below the Chandra X-ray limit, and it cools over billions of years like a dense ember. In this outcome, the place where a star dies becomes a compact, Earth-sized core surrounded by space that has been enriched by the star's own lost atmosphere. It is quiet, but it is not empty. It contains a remnant, a record of a long stellar life compressed into a small volume. In more massive stars, the transformation is far less forgiving. Massive stars build layered interiors, an onion shell structure of successive fusion stages, each one requiring higher temperatures and producing heavier elements. This nuclear progression ends at iron, where fusion can no longer provide energy. When an iron core forms, the core can no longer support itself through fusion, and collapse begins. In those final moments, nuclear physics, particle physics, and gravity collide in a single event. Photodisintegration consumes energy by breaking apart heavy nuclei. Electron capture reduces electron degeneracy pressure and floods the core with neutrinos. The core collapses rapidly until matter reaches nuclear density, at which point neutron degeneracy pressure and the strong nuclear force push back. A shockwave forms. Neutrino heating helps drive an explosion, and the star's outer layers are expelled in a core collapse supernova. In this outcome, the place where a star dies becomes an expanding remnant of energized gas and newly formed elements. The surrounding region is shocked, heated, and enriched. The death site becomes part of the chemical evolution of the galaxy, scattering oxygen, silicon, iron, and many other elements into space. And at the center, depending on mass, one of two compact remnants remains: a neutron star or a black hole. A neutron star is what happens when collapse is halted one step deeper than a white dwarf. Electrons have been forced into protons, forming neutrons. The core becomes neutron-rich matter compressed to nuclear densities. Neutron degeneracy pressure, again rooted in the Pauli exclusion principle, resists further collapse. The object is small, tens of kilometers across, yet carries a mass comparable to the Sun. It may spin rapidly because conservation of angular momentum tightens rotation as the core shrinks. It may carry an immense magnetic field, intensified by compression. It may beam radiation from its magnetic poles and become a pulsar, pulsing across space with extraordinary regularity, as Jocelyn Bell Burnell's discovery first revealed. Here, the place where a star dies can become a lighthouse. It can become a gravitational anchor at the center of an expanding supernova remnant, still influencing its surroundings through radiation, particle winds, and magnetic fields long after the original star is gone. But if the collapsing core is too massive for neutron degeneracy pressure to hold up, collapse continues. This is where black holes appear, and the story shifts from the behavior of matter to the behavior of space-time itself. In general relativity, gravity is the curvature of space-time caused by mass and energy. Carl Schwarzschild's solution revealed that if mass is compressed within a certain radius, an event horizon forms, a boundary beyond which no signal can escape. The Schwarzschild radius marks that threshold for a non-rotating black hole. When a stellar core collapses past this point, the place where the star dies becomes defined by an edge that cannot be crossed outward. Light can no longer return. Information can no longer be sent back into the wider universe. And yet, even then, the region is not erased. The black hole's mass remains gravitationally present. Its environment can still glow if gas falls inward and heats in an accretion disk. It can launch relativistic jets. It can merge with other compact objects, sending gravitational waves outward, ripples in spacetime that can be detected far away. The Event Horizon Telescope has shown what such extreme curvature can look like around supermassive black holes, revealing a shadow framed by glowing gas, consistent with the predictions of general relativity. So across these outcomes, a pattern emerges. Stellar death is not disappearance, it is transformation. The transformation is guided by gravity, which never stops pulling. It is constrained by quantum mechanics, which limits how matter can be packed and provides degeneracy pressure. It is powered and shaped by nuclear physics, which determines which fusion stages are possible, which elements are built, and where the energy support finally fails. A star dies where these domains intersect, not as separate subjects, but as one connected system. Gravity sets the stage, fusion holds the balance, fuel depletion breaks the balance, collapse begins. Quantum rules resist, nuclear reactions shift, neutrinos escape, shock waves expand, matter is expelled, remnants form. And in each case, the place where a star dies becomes something that can change its surroundings. A planetary nebula adds enriched gas gently and paints space for a short time with glowing shells. A supernova remnant slams energy into its neighborhood, compressing clouds, triggering new star formation in some regions, and scattering heavy elements outward. A neutron star can become a pulsar, illuminating its environment in radio waves and high-energy emission, and acting as a gravitational and magnetic engine. A black hole can reshape the motions of nearby matter, feed on gas, launch jets, and merge to produce gravitational waves that carry the signature of that death into the wider universe. Even the quiet, long-term fates fit this theme. White dwarfs cool toward darkness over spans longer than recorded human time. Neutron stars spin down and become less active, but remain as dense gravitational objects. Black holes may, according to Hawking's idea of Hawking radiation, evaporate over unimaginable timescales, suggesting that even the darkest remnants might not last forever. So when returning to the central question, the answer can be held gently, without drama and without simplification. Where a star dies, space becomes enriched, reshaped, and populated by remnants that can persist for eons. Where a star dies, physics reveals its most basic rules, because the usual layers of comfort are stripped away. Where a star dies, the universe does not merely lose a light, it changes form. And that change is not rare. It is one of the main ways galaxies evolve, one of the main ways elements travel, one of the main ways the cosmos turns long-lived stability into new structure. A star's life is an extended negotiation. Its death is the moment the negotiation ends. And what remains in the place where that star once shone is not nothing. It is a new object, governed by gravity, quantum mechanics, and nuclear physics, carrying the story forward, quietly and relentlessly, into the next era of the universe.